In this video, I am going to explain the principle of operation of SCR and the voltage and current characteristics of SCR. SCR is a 3-terminal, 4-layered, 3-junction, solid-state, fast-switching semiconductor device. Symbolically, SCR is represented like this. It has 2 electrodes called as anode and cathode. This is anode and this is cathode, and there is another terminal called as gate. The internal structure of SCR is, it has 4 layers and 3 junctions. This is P, N, P, N. So the layers of an SCR in its structure is formed like this, PN, PN. Here we see 2 similar type of layers, 2 P layers and 2 N layers. This P layer is called as outer P layer. This P layer is called as inner P layer. This N layer is called as outer N layer. This N layer is called as inner N layer. The electrode which is connected to the outer P layer is called as anode. There is an electrode connected to the outer N layer which is called as cathode. There is a terminal connected to the inner P layer is called as gate. This is gate terminal. Right? So SCR is symbolically represented with anode and cathode and gate. And the internal structure of SCR is, it has 4 layers and 3 junctions. These junctions can be named as J1, J2 and J3. That is why SCR can be defined like this. SCR is a 3-terminal, 4-layered, 3-junction, fast-switching, solid-state semiconductor device. So that is nothing but SCR. Now here there are 4 layers. Outer layers, outer P layer and outer N layers are heavily doped material. And inner layers like inner N layer and P layer are lightly doped. Okay, so this is the basic structure of an SCR. Now I would like to explain the principle of operation of SCR with the help of 3 states. Number 1, forward blocking state. And number 2, forward conduction state. And number 3, reverse blocking state. The principle of operation of SCR can be simply understood with the help of these 3 state of operations, right? Number 1, forward blocking state. Number 2, forward conduction state. Number 3, reverse blocking state. Now let us see what is forward blocking state. You know, in order to understand the forward blocking state, we need to just apply a voltage across anode and cathode. Let us assume that there is a DC supply given across anode and cathode. When this positive polarity is connected to the anode, we call it as the terminal anode is made positive with respect to cathode. So that means it is positive and this is a negative. Or we can say like this also. Anode is connected to higher potential compared to cathode. So whenever anode is connected to higher potential compared to cathode, here junction J1 and J3 are forward biased and junction J2 is reverse biased. Then device is under forward bias condition. So whenever device is under forward bias condition, the junctions J1 and J3 are forward biased and junction J2 is reverse biased. Because of this reverse bias, there is a depletion layer formed at this junction. This is the depletion layer. So there is no current flowing from anode to cathode even though there is a voltage applied across it. So that means device still in blocking state. There is no conduction. Conduction is not happened. So that is why that state is called as forward blocking state. Forward blocking state. Now let us see how here forward bias is formed as junction J2 and junction J3 and reverse bias formed at junction J2. Whenever forward bias occur across this SCR, here this higher potential or positive polarity, okay, repels the majority carriers of this P layer called as holes. Holes are repelled. Right? When holes are repelled by the force of this higher potential, these holes will cross this junction. So suppose if majority carriers of this P layer are crossing this junction, means this junction is under forward bias. At the same time, similarly we can see another one. See here it is a N layer connected to the lower potential. That means this negative polarity repelling the majority carriers of this N layer called as electrons, okay, away from this electrode. So that is why here the majority carriers of this N type material are crossing this junction here. Then we can call it as forward bias. So at these two junctions, okay, there is a forward bias occurred, but whereas junction J2 is forming a depletion layer. Why it is forming depletion layer? You know, whenever these holes are crossing, this is due to recombination of majority carriers of this N-type material with the holes of this P-type material. So that means, you know, the majority carriers of this N-type material are in this direction. Okay, in this direction. So here also similar happens. Here majority carriers of the outer N layer is in this direction, means here the majority carriers of this inner P layer called as holes are getting recombined with the free electrons. That means here all free electrons are towards upward direction. Here all free holes are towards downward direction. So that means here the depletion layer is increased. The width of depletion layer is increasing. Suppose if I increase the electromotive force across this anode and cathode, that is EMF, right? Then what happens, you know, this depletion layer will increase further. So when this depletion layer is increased further, that means here there is a reverse bias formed. So because of this reason, there is no current flowing through this SCR from anode to cathode because of the reverse bias occurred during forward bias of this SCR. So that is why this state is called as forward blocking state. Then what to do? So how to make the device to get conducted? So during forward bias voltage, right, if we keep on increase the voltage applied across the anode and cathode, and this depletion layer will increase and increase, you know, then there will be breakdown occurred. So when breakdown occurred, the reverse bias is converted into forward bias, so that there is current flowing from anode to cathode. Then we can say that device is in on state. Device is said to be on state, right? So if it happens during forward bias condition of this SCR, then that state is called as forward conduction state. Here we have connected a gate terminal to the inner P layer. Through gate terminal we can apply the voltage. So the voltage applied across the gate terminal is very less. So that is applied across gate and cathode terminals. Here gate signal is a very low signal. It is a low power signal. So when I apply gate signal or gate pulse, if it is positive with respect to cathode, right? So then here holes are repelled. In this gate connected region, holes are repelled from here. So at the same time, These electrons are, right, electrons are attracted towards the repelled holes. So here with the help of gate pulse, the width of the depletion layer gets vanished. So whenever depletion layer gets vanished, then here this reverse bias will become forward bias. So next one is reverse blocking state. Here the voltage applied across anode and cathode is reverse. That means cathode is connected to higher potential with respect to anode. Or we can say like this, cathode is connected to positive polarity of the source with respect to anode. So at this situation, junction J1 and J3 are reverse biased and junction J2 is forward biased. Because of this reverse bias of J1 and J3, there is no current flowing through the device from anode to cathode or cathode to anode. So that is why this state is called as reverse blocking state. Now I am going to explain the VI characteristics of an SCR. I am considering the voltage on x-axis since it is independent quantity. Now see here, during forward blocking state, there is voltage applied across the device. So this voltage is getting increased, right? Whenever positive polarity connected to the anode, that means the higher potential connected to anode with respect to cathode, there is voltage applied across anode and cathode terminals, that is called as positive voltage. It is increased to the instant where avalanche breakdown occurs. As long as I keep on increase the voltage across the device, that means dV by dt is getting increased. At one instant, the depletion layer gets vanished. The voltage at which depletion layer is vanished is called as forward breakover voltage. So this is known as forward breakover voltage, VFBO. So when depletion layer is vanished, the reverse bias at junction J2 is converted into forward bias and the device gets turned on. When the device gets turned on, the voltage across the device gets fallen and the current through the device increased. With the help of avalanche breakdown voltage, device is turned on during forward bias condition. So as soon as device is turned on, the voltage applied across the device, that means device voltage suddenly gets fallen and the current flowing to the device will increase. This region is called as forward blocking region. So this is called as forward blocking state. During this region, device still in blocking state. This is the region that is forward conduction state. Forward conduction state. So device is converted to forward blocking state to forward conduction state with the help of here forward breakover voltage or avalanche breakdown voltage. But avalanche breakdown voltage is not practicable because the high rate of dV by dt triggering, may be sometimes greater than that of the specified dV by dt rating of the SCR. So device may be subjected to damage. So that is why before forward breakover voltage is occurred, device has to be turned on. So in order to turn on the device, before forward breakover voltage appeared across the device, the gate pulse has to be given. So with the help of gate pulse, what happens here, with the help of this gate pulse, the device is turned on earlier, right? Suppose if I apply gate pulse at this particular instant, device will be turned on. Right? So that means, forward breakover voltage is decreased here. Right? Forward breakover voltage is decreased here. Suppose if it is forward breakover voltage 1. So similarly, here, device may be, that means the gate pulse may be given at this particular instant of forward voltage, forward bias voltage. So that may be taken as, another forward breakover voltage. So here also I may consider like this. So this is another FBO. Now you see here, suppose if it is forward breakover voltage VFBO1, this is forward breakover voltage 2, this is forward breakover voltage 3 and this is forward breakover voltage 4. When gate pulse is given earlier and if the magnitude of gate pulses or gate current is higher, the forward breakover voltage is reduced. That means, the avalanche breakdown voltage is decreased with the help of the gate pulse and its magnitude and its duration, right? So at this particular instant of forward bias of SCR, I have given gate pulse and device is turned on at this instant itself. Whenever gate pulse is given, device is turned on. So that is why up to this instant, whatever the voltage, forward bias voltage applied across or appeared across the device will be fallen down and the current gets increased, right? So that means here I can say that at this particular instant, right, this is nothing but gate current 1 and this is nothing but gate current 2 and this is taken as gate current 3. Now you tell me gate current 3 is greater than that of gate current 2. Now see here the magnitude of current. So here current magnitude we can see. So at this particular instant there is. So that means here gate current is increased. Okay. So at this particular instant gate current is IG3. So that means here IG3 is greater than that of IG2 and greater than that of IG1. Okay, let us consider this instant IG0. That means there is no gate signal applied. So that means there is no gate signal which is equal to IG0, which is equal to 0. Right? So here, when gate current is increased, the forward breakover voltage is decreased. Okay, if you further increase the gate current, and forward breakover voltage will be further decreased. Right? So this is how here we can apply the gate current. Now here we need to understand something, that is here the current at this point is called as latching current, and the current at this particular point wherever it is getting turned on is called as holding current, right? So now you see here holding current, latching current. There are two currents introduced in this voltage and current characteristics of SCR. What is meant by holding current? What is meant by latching current? So now you see here holding current is the minimum anode current, the minimum anode current below which device will be turned off. You see here, this is the minimum anode current. So this is what IA is nothing but anode current. So this is minimum anode current below which, right? If you consider here, let it be like here. So that means wherever forward breakover occurs, right? So below which, so the minimum anode current below which device gets turned off, right? Device gets turned off. So then here see, this is the latching current. Latching current is the minimum anode current, which maintained or which keeps the device still in on state even after removal of gate pulse. See here, up to this instant we have applied gate pulse. So this is the gate pulse. Even after removal of gate pulse also, this is the minimum anode current which keeps the device still in on state. So on state, below which we may see that device may be turned off at particular instant. So that is why here we can see that there are two types of currents in SCR, that is holding current and latching current. So holding current is the minimum anode current below which SCR is turned off. Latching current is the minimum anode current which keeps the device in on state, remain in on state even after removal of gate signal, and which is greater than that of the holding current. Right? So this is nothing but latching current. So this all happens during forward bias condition of the SCR. Now let us consider reverse bias condition. So when supply is reversed, that means whenever anode is made negative or cathode is made positive with respect to anode, then here we see that J1 and J3 are reverse bias, J2 is forward bias, so that there is no flow of current through the device, which is called as blocking state. So during reverse bias condition of SCR is in blocking state. That means SCR is in off state. So that is why this is called reverse blocking state. So we can consider it as reverse voltage applied now. So that is why we can say this is the reverse voltage applied across the SCR. So at this particular instant, which is called as reverse breakover voltage. At this reverse breakover voltage, okay, SCR has a current flowing through it that is in reverse direction. Okay, during this period we can call this one as a reverse blocking state. So reverse blocking state of the SCR, right? RBS of SCR, right? So this is the VA characteristics of SCR. Thank you.
ఈ వీడియో కానీ మీకు నచ్చినట్లయితే లైక్, కామెంట్, షేర్ చేయండి. మరిన్ని అప్డేట్స్ కోసం సబ్స్క్రైబ్ చేయండి.